So today, what is it, it's March, yay, 3/2/21. So our objective today is really to talk about functions. We're going to talk about the definition, of a function, and we want to talk about domain and range. Okay, so I'm going to give you a more mathematical definition of a function. We've talked about what a function is before, where every x value is paired to only one y value, right? We've said that before. X value can only be paired to one y value, but now we're going to get more specific. We're going to say where every element of the domain is paired to exactly one element in the range. Okay, that's the definition you're probably going to see in most math books. What does it mean? Well, it means basically that every x value can only have one y value, okay? And then, I don't know, you guys remember my latte story, right? Lattes. Right, here's my latte stand, one latte, and you really wouldn't pay two different prices for one latte, right? Or if that's one t-shirt, you wouldn't pay two different prices. One price, one t-shirt. One price, one latte, okay? But then if we think about what the domain is all x values, right? Domain is all x values, or a control variable, and the range is all y values, or our dependent variable, then you get the same thing. So I can control, like, we got to be careful we don't call it x values, because, I mean, this problem could be lattes, number of lattes. That wouldn't be an n, or that wouldn't be an x, that'd be a number of lattes. So I can control, you ready? This is my control variable. I get to control how many lattes I buy, correct? Let's just draw this better so it makes more sense, right? I can buy one, I can buy two, right? I get to control, that's the x values, how many lattes I buy. But then the price is dependent, you ready? The price is dependent on what I choose. So I get to control this, and the price is dependent on what I choose, okay? So let's say that's $5, okay? There we go. Does that make sense for a control variable and dependent variable? Vertical line test, you guys have seen that before. So in this case, this one fails the vertical line test. So anywhere, if you can draw a line straight down anywhere, if it touches the graph in more than one place, it fails the vertical line test. This one would pass the vertical line test because it hits it only once, right? The vertical line test is just simply a test where you draw a vertical line, and if it hits it in more than one place, it's not a function, okay? Zeros, define zeros. Zeros are any value of that makes p of x equal to 0, okay? Any value. So we got to be careful because we've seen I answers can be 0. So let me go back to our warm-up, okay? Real quick, our warm-up. That's a 0. Believe it or not, if I plugged it into here, the answer would be 0. It really would. Okay, hold on, I'm sorry. That 2 is a 0, because if I plug 2 in for x, and I'm not going to do it, but I know it will be. If I plug 2 here, 2 here, 2 here, it'll make it 0. If I plug negative 2 here, 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 it'll make it 0. And if I plug 16/3 in for x, it'll make it 0. So these are called my zeros, okay? And then sometimes we even have I answers, right? Like on our test. Those are also zeros, so if we plug those in, we'll get an answer of 0, okay? All right, domain. Well, before we do anything, we got to write down something on the side, okay? First of all, don't divide by 0. ever. I think they took the feature off. It's kind of sad, but let's see if it's there. Last time I asked, they didn't give it to me. What is 0 divided by 0?
Imagine that you have 0 cookies and you split them evenly among 0 friends. How many cookies does each person get? See, it doesn't make sense. And Cookie Monster is sad that there are no cookies. And your friends are sad because they don't exist. Oh wow, this escalated quickly.
Thank you. So, Cookie Monster gets sad if you divide by 0. Okay, now, you can't divide by 0 simply because if you keep dividing by smaller and smaller and smaller and smaller pieces, like take one sheet of paper, and you keep dividing this one sheet of paper into smaller and smaller and smaller and smaller pieces, you can even go to an atom, right? And you still have pieces, right? You can even go beyond an atom to like quarks or whatever, and you can still have pieces, right? But it's absolutely impossible to have a size of 0. Does that make sense? We do know this, though. As we get closer to dividing by 0, as we get to 1 divided by 0, we'll approach infinity, okay? That's one of those things, okay? Now, the second thing we got to talk about is this, okay? We don't divide by 0, and for real numbers, we don't take the square root of a negative number, okay? Okay, for real numbers. We've done that before with imaginary, but imaginary numbers are imaginary, right? They're not real. So when we talk about domain, we're talking about the domain in the set of real numbers. So if I take a look at example 1, right off the bat, and I can graph this too, I'll show you what I do when I graph it. Right off the bat, I know this, that x cannot equal negative 4. You okay with that? And just to show you what happens when I divide by 0, hold on, 1 divided by x plus 4. Well, let me get a decent one. I got to get a better window. Zoom. There we go. What's happening at 4? At negative 4, it just kind of flips out, right? Well, what happens is it's going to infinity, and it's going to negative infinity. So here's a great example. Now, does it equal anything else? Sure. So the domain on number 1 is, well, we could say x equals all real numbers, because it equals everything, except x cannot equal negative 4. Okay, does that make sense, everybody? Right? It can equal anything. You can plug in any number you want for x, any, but don't plug in negative 4 because you divide by 0. Okay, example 2. Well, I do know that if x were negative 5, I'd be in trouble, correct? Negative 5 plus 4 can't be negative 5. It can be 4. You guys agree? It can be 4. But it can't be can't be like a negative 4.1. So I'm going to say that x is going to be, has to be, greater than or equal to negative 4, okay? It can equal negative 4. It can equal negative 4 because square root of 0 is 0. That's okay, right? And then, again, if you take a look at the graph on this, I think it's always good to look at the graph. Square root of my x plus 4. I graph it. See, there it is. It starts at, for x, starts at negative 4 and goes forward, okay? Now, how about this one? Well, can x be 3? Yeah. Can x be 4? Can x be 4? No, x cannot be 4. X can't be 4 because if x is 4, you'd have 9 minus 16, and you have a square root of a negative number, okay? Can x be negative 3? Can x be negative 3? Can x be negative 4? Think about it. If x is negative 4, you have the square root of 9 minus a negative 4 squared, right? 9 minus a positive 16. Ooh, that's bad, right? So here's what I know. X is going to be in between. And I like interval notation. Two ways to write this. I can say negative 3 is less than or equal to x, which is less than or equal to 3. That's in set notation. Or a new way to write this in interval notation. Okay, that's interval notation. I like interval notation. It's easier to write. Okay. So if you use a bracket on interval notation, means equal, right? Parentheses is no equal, okay? Now take a look at this graph. This is actually kind of interesting because you'll see it's a half circle. Okay, so if I go square root of 9 minus x squared, okay? If I graph this, sure enough, it's a half circle, right? And it does exist between negative 3 and 3. See that? All right. 4, okay? So if I take a look at 4, oh, I know one thing. I can't divide by 0, right? So there can be some x value in here that I can plug in and divide by 0. So I don't want to divide by 0. So first of all, I'm going to factor this one. I can factor the bottom, so I'd have an x plus 2. Factor this into, let's see, an x minus 4x plus 2, right? So I just factored my denominator. And then if I look at it, it's like, wait a minute. X cannot equal 4, right? And x cannot equal negative 2. You guys agree with that? Now you might be able to cancel out the 2's and say, well, cancel, I don't need to worry about this. But in the original function, it's there. You agree? Now this one's a weird graph. Wait till you see this one. It's really weird. We're going to talk about this. This is something in calculus. When you guys see calculus, we're going to talk a lot about this graph. X plus 2 divided by parentheses x squared minus 2x minus 8. Let me graph this one for you. Okay, graph. So I want to show you something, okay? So I did say it can equal 4. So see how it goes crazy at 4? It goes off to infinity, right? Because you divide by, but then what's going on at negative 2? So if I go to trace, negative 2. Watch. Everybody watching? Do you see something weird? Does something strike you as odd when I plugged in negative 2? Anybody see something odd? Spencer, what do you see?
There's no y value.
There's a hole there. Now, how big is the hole? There's a y value. There's a hole there. But technically the hole, watch you guys, watch. Technically the hole is that wide. Okay, does that make sense? Because I can have a negative 2.1, I can have a negative 2.11, I can have a negative 2.000001, but if right at negative 2, we have a hole. So there's a hole there somewhere, okay? So what's my domain? Well, my domain I'd say is x equals all real numbers, equal everything. And that's my symbol for all real numbers, except x cannot equal 4 and x cannot equal negative 2. Weird, huh? Okay, example 5. We're not going to let example 5 bother us, but I do know this one's got 2 problems, okay? 2 problems. So if x is 1, 1 minus 1 is 0, right? Well, that's okay as far as square roots, but then you get 0. So x in this case has to be greater than 1. Not equal to, because if it's equal to, then we get a 0 and you can't divide by 0. Okay? And if I looked at that graph, you guys will see it. Y equals 7 divided by parentheses, square root of x, subtract 1. Let's see what this graph looks like. Okay, so what happens at 1? Well, go to trace. What's happening at 1? First of all, right, if I go to trace 1, let's go trace 1. Again, same thing, right? There's no y value. So it goes off to infinity. You have to get to infinity to get to 1. I'll say it again. Crazy, huh? I got to get to infinity for x equal 1. Well, that can't happen. It's impossible, right? Can't get to infinity. Infinity's like love. It's just an idea, huh? It's not a real number. Okay, turn page. Example 6. Determine the domain, range, and zeros. Now, I don't know if you guys remember the absolute value graphs. It's been a while, but let's see if we can do an absolute value graph. It's been a while since we've seen these. Hold on. Let me get a piece of graph paper out. tape that down for a second. It's been a while since we've seen absolute value graphs. Absolute values are the V's, and the reason the absolute values are a V is because whenever it becomes negative, it bumps up to positive, okay? So the vertex of this one, it's got to be at -3, -4. And I don't know if you guys remember that from Algebra 2 and Geometry. We've talked about this quite a bit. You can also graph this on the calculus, and I'll show you in a second, okay? So give me a moment. I'm going to go ahead and let me get this. Let me get this. Okay. Okay, so my absolute value function looks like this. Right? And you can actually put it in your graph. You just have to be careful how you put it in. Y equals clear math, ABS. See, I'm good on these, aren't I? X plus 3, and then minus 4. Let me go ahead and graph for you there. There it is. It's exactly what I have, right? You guys agree? So, domain. Well, how wide is this graph? What do you think? Domain. How wide is this graph? How wide is this graph? Oh, it's got arrows on it. How wide is this graph? Forever, right? It's forever wide, so the domain's got to be every x value, because as it moves over, the graph's still going, right? So the domain is x is equal to all real numbers, because it goes forever in both directions. The range, right, is just the y values. There are no y values on the graph down here at all possible y values. So the graph starts at a y value of -4 and goes up. Y is greater than or equal to -4, okay? My zeros are here and here, okay? So my zeros, x equals 1 and x equals, let's see, what is this? 1, 2, 3, 5, I think 6, 7. Isn't it 7? I think it's 7, -7. Okay? How am I doing? Last problem. Okay, this takes us back to geometry and algebra 2. It's a piecewise graph, all right? So if it's been a while since you guys have done this, I'm going to help you. The first thing I do is I put in my border points. Okay, remember doing this? So I have 3 graphs that are all going to be connected. But all 3 graphs are within these boundaries, okay? So the first thing I do is put in my boundary lines. So at -1, -3, 2, and 5. Now these are invisible. I have these boundary lines. Okay, they're invisible, but I like to use a marker because then I can see them, okay? These are like my boundaries. Okay? That's the first thing I do when I do a piecewise graph, so I just draw my boundaries, okay? Now the first graph, y equals x, just write that down, graph 1, y equals x. Well, that would start at, and I'm using my pencil because I might have to do some erasing here. Starts at 0, right? Because that's a, 1, x plus 0. I'm going to start at 0, up 1 or 1, up 1 over, okay? So here's my graph. Except this graph only belongs in here. This graph only belongs in here. So I'm going to erase the other part of this graph because I only want a piece of it. That's why they call these piecewise graphs. I want a piece of it. I want to make sure that I put a solid dot here and an open dot here. Solid dot because it equals it at -3. Open dot at -1, okay? How am I doing? Am I going too fast? Okay. So my second graph, graph number 2, is y equals x squared minus 1. I know that's a parabola, and it's going to look like this. 1, 2, 3, 4. And so my parabola looks something like this, right? Except, of course, I only want this parabola between -1 and 2, so I only want it in this region here. So I don't need these other regions at all. So I'm going to erase this part here, right? Erase this part here. It only exists there. So I'm going to go ahead and put a solid dot here and an open dot here. Okay. And then third graph is y equals 2. That's a horizontal line at 2. So I would graph it at 2. All the graphs like that, except I don't want all of this graph. I only want the piece that's between 2 and 5, right? So I'm going to erase all the rest of this. Don't need that. And I don't need that. Okay, so I'm going to put right in here at 2. I'm going to put a solid dot and an open circle because it equals it at 2. But it does not equal 5. Now, it's super important. I think you guys understand why I have to have solid dot, open dot. Otherwise, it would not be a function. You have to have this. And you have to have this. Otherwise, it would not be a function, right? Okay, so finally, domain. Well, this graph goes from -3 over 5. In fact, the easiest way to get the domain on this is the domain is actually here and here. It really is. There's your domain. It really is from -3 less than or equal to x, which is less than 5. Or if you put it in interval notation, which is what I like, I'd go -3 comma 5 like that. That's interval notation. It's easy to write. Okay. Range. Let's see. Starts at a height of -3, right, and goes almost all the way up to here to 3, right? So my range is going to be from -3 is less than or equal to y, which is less than 3, because it doesn't quite touch here at 3, does it? Almost. Or in interval notation, I would go -3 comma 3 with a parentheses because no equals. Okay. All right. That's all I have for today. That's pretty good. I think you know